Okay, so far we have 34 students only. Let us wait for 1 or 2 minutes, then we can start our discussion. So inform all the students we have a 10 minutes of relaxation is there for each and every subject. So please be on time. Okay. So at sharp 11 o'clock, we have to be all should present. Okay. Because the previous semester we don't have any time to switch to another session, but you have a plenty of time is there to attend the next class. Okay, you please come to the class in time. As all of you know that the attendance will give you the best score in your subject, as all of you know that. A sharp 11:05 I'll start. So all these recordings, all these lectures are recorded. So you have to be careful about it. I hope the board is visible, I think, right? The note is visible to all of you, right?
Yes, sir.
Yeah, fine. So it is called, let us consider, in the last class we have seen only some introduction, and now we are going for the actual discussion. Okay, so it is the lecture number 1. The date is, as you know, that the date is 2021. The course name is Digital Design through Verilog HDL. Okay, so please remember that what we are doing here is that digital designs that we are using by using Verilog HDL, right? Whatever the digital designs that we have done in the previous semesters, the same designs that we have to do with the help of Verilog HDL. Okay, that is what the topic that we have to consider in this semester. Okay. Okay, let me check how many are there. 43 students are there. Fine, no problem. Okay. As I mentioned that we are talking about the digital designs with the help of Verilog HDL. First of all, let us recapitulate what is the digital design, or I can say that the conventional digital design, right? So I can say that conventional. What do you mean by this one? So as all of you know that the conventional digital design stands for That means we have to realize the idea. That is what actually involved in the digital design. Whatever the idea you have in your mind, that must be realized with the help of gates. Okay, so in order to do that, one idea is translated into a real hardware or real device. What are the things that are involved in this one? That is called design process. Okay, so what do you know by design process? So the design process consisting of functionality, functionality of the device. Okay, so the functionality of the design that we should know. So what do you mean by the functionality of the design? The functionality of your circuit that we should know first of all. Okay, the functionality can be represented by, in general, we have to use truth tables, right? So truth tables that we have to use, right? So with the help of the truth tables only, we can identify the functionality. Okay, that is what the first step. If you want to design any circuit, we should know, right? Now, this functionality is translated into mathematical equations. Mathematical equations. Okay, so therefore, whenever we have a functionality, we know the truth table. From the truth table, we have to develop the mathematical equations. How do we do this one? So this is done with the help of Boolean equations, Boolean algebra. With the help of Boolean algebra, right? So, or any other method that we can use. Generally, we have to consider the Boolean algebra only for the digital circuits, right? Once we know the mathematical equations in the form of SOP or POS form, then what we have to do, we have to draw the circuit diagram, right? We have to draw the circuit, right? With the help of some basic gates. Okay, so we know the gates. According to the gates, we can draw the circuit diagram. Okay, so how do we do this one actually? So with the help of pen and paper, right? With the help of pen and paper. Okay, once the circuit is there in your paper, then we have to go to the lab. We have to go to the lab and place the components on the breadboard. Okay, so therefore placing the components on the boards, on the breadboard, and make the necessary and make the necessary connections among the devices also we should know, right? So therefore, for this one, what we have to do is that we have to consider the breadboards. So therefore, the breadboard is the one of the important thing, breadboard. We have to consider the breadboards. Okay, so this is what the conventional design flow look like, right? So from the idea to actual breadboard connectivity circuit will be the process of designing the things. Okay, so I can say simply all these things, whatever the things that I'm talking about, these are called design process. Design process. Okay, so therefore the design process involves idea picturization and converted into mathematical equations, converted into diagram, converted into a realistic breadboard connectivity among the devices, among the components. So this is what actually we do in our laboratory. Okay, so this design process, okay, so this design process is acceptable. This design process is acceptable for or suitable for small digital circuits. Okay, small digital circuits. Are you agree with me? So these things are acceptable for the small digital circuits. Whatever the design process we do here, that is acceptable for small digital circuits. Let us consider one example. For example, for example, if you consider, in the last class I told you that let us consider a full adder. How many inputs it is having? Three input signals which you should have, and two output signals you should have, sum and C out, right? Okay, so how many number of components you generally will have this one? Okay, what is the size of the truth table? The truth table consisting of 2 power 3, 2 power 3 columns, 2 power 3 rows will be there. That means 8 combinations will be presented. That is the size of the truth table. How many number of components generally we use? What are the components generally we use? So three input, one exclusive OR gate is required, and three AND gates are required, one OR gate is required, approximately. Or worst case, we can say that two input exclusive OR gates and two input, two AND gates and one OR gate. Altogether, that is four, five, six gates are required. Okay, so that means worst case 6 gates are required. Okay, that is the size of the truth table. This is the number of gates, right? So therefore, for this particular complexity, it is possible to go to the laboratory and make the connections among these 6 gates and necessary connections among the gates, and we can utilize the breadboard as our designed circuit, right? But what if the complexity of the circuit is increases, which means that if an adder consisting of 8 input signals, another input is having 8 input signals and one CN signal, and some signal should be of course an 8-bit size, C out is 1 bit size, right? C out. Now this is the A and B. Now can you define what is the input, the truth table size it is? So the number of inputs are 8 bits and one input, one bit size. Therefore, 2 power 9 is the truth table size. That means these many number of rows that the truth table consisting of. And of course, more number of gates are required, more or huge number. I can say that more and more number of gates are required, right? So if the complexities increases from simple 1-bit full adder to 8-bit adder, it is not possible to go to the laboratory and make the necessary connections among them. Are you agree with me? Fine. So in that situation, we have to go for another approach. It is called complex digital design. It is called complex digital design. Okay, so don't think that complex is not a mathematical word. The complex in the sense the content in the digital circuit is more and more. Okay, the digital circuit consisting of more number of components. So in that sense, we are talking as complex digital circuits. For a complex digital circuit, what will happen? For the complex digital circuits, what we will do is that we have to use HDL programming, HDLs that we have to use, HDL. Okay, so a programming language that we have to use to notice the functionality of the design. Okay, if you want to have, if you have a functionality, that functionality must be represented in the form of a language. Earlier that will be represented in the form of a truth table, but here we are writing in the form of a truth table. It is in the form of a language. Clear? And with the help of this one, with the help of this one, we have to consider a computer aided design tools, CAD tools that we have to use. Okay, so once your design is in the form of a language, and we have to use the computer aided tools, computer aided design, we normally call it as CAD tools that we have to use. CAD tools, I can say that. CAD tools that we have to use. Okay, and so once we have designed in the by using the help of the tools, then we have to place these kind of things. Then we have to place our design either in the PLDs or FPGAs, right? So this is what the process is in design process involved in the design process involved when the complexity of the digital circuit is increases, right? Okay. So CAD stands for CAD. CAD stands for computer aided design. So what do you mean by the computer aided design? We will see later on. Okay. Similarly, PLDs is nothing but programmable logic devices. Okay. FPGA stands for field programmable gate array. Okay. So that means instead of the breadboard, we have to use either PLDs or FPGAs. Okay, the same design process we are using, but in the form of this method. Okay, so yeah, how we can implement our design in the FPGA, all these things we will see in the coming classes. Don't worry about it. Okay, just you have to keep in your mind that whatever the digital circuit is there, the digital circuit must be represented in the form of a language, and that must be drawn with the help of CAD tools, and the drawn circuit must be implemented in the FPGA or PLD, right? So far, so good. Okay, so this is called, normally people will call it as, this design process, people will call it as FPGA design, FPGA design. ఏమంటారు దీన్ని మనం FPGA design. Okay, so therefore, whenever we have a complex digital circuit, complex digital designs, if you want to go for it, then that digital design is called FPGA design. Okay, so I will tell you, I will show you what is an FPGA, its diagram later on. Similarly, I will show you what are the CAD tools are available. And in our course, we talk about HDLs. How do we describe a circuit with the help of HDLs? Okay, is it clear to all of you what is the difference between the conventional digital design and complex digital design so far? If it is clear, then you please type it as in the chat box. So you have to remember two things. What is the conventional digital design? Complex digital design. Okay. So please remember. So whatever the things that I am discussing in the class, you please, all of you, please put your concentration what I am discussing. So if you are not putting your concentration what I am teaching, then it's very difficult to pass the subject and identify this subject is making it, you cannot say that this is easy subject. So if you follow my instructions and clearly understand the concept that I'm discussing, it is a dead easy subject. Okay, even though it is a programming language, you can understand very, very easily. Just you have to put your concentration. Once you know this language, then it is possible to it is possible to take the projects in your final year. Okay, and there is a lab is also there. As in this particular class, I'm not going to talk about the CAD to the lab information, but if time permits me, we are mainly focusing on hardware description languages only. Okay, so what is the how can we write a digital circuit in the form of a language, that we focus mainly on this particular course. But if time permits me, how to use this code to run the circuit by using the CAD tools, and how do we implement that is in the FPGA, that we will see later on. but actually these two, so these two parts is actually the lab part. So VLSI lab is there, so we focus mainly on VLSI lab, but if time permits me I will do it here. But this is actual our course, so hardware description language is our course. Okay, the course is mainly dealing with HDLs only. Okay, but overview is that it's an FPGA design. Okay, now so far so good. Now let us consider another one. So what do you mean by, as I mentioned that we are talking about HDL, right? What do you mean by the HDL? What it says that? So it is actually hardware description language, right? HDL stands for hardware description language. Okay. Okay, fine. What do you mean by this one? Generally, whatever the digital circuit, so any digital circuit we are treating as any digital circuit, we are treating as SKT stands for circuit, for example. Any digital circuit we are treating as a hardware. Okay. Okay. So this digital circuit must be described. It must be described. It must be described by using a language. By using a language. Okay, that is a very, very important thing is that. So we come to the point is that a language we have to use, a language that we have to use, a language we have to use to describe a digital circuit. Okay, as simple as that. Right? Now, if you want to describe any digital circuit, how do we look at the digital circuit? That's an important thing. So the next point to remember here is that digital circuit visualization. Digital circuit visualization. Okay. How do we visualize your digital circuit? That's an important one. Okay. So generally there are the two ways are there. Generally there are the two ways are there. Okay. So two ways we can look at any digital circuit, right? Okay. So what are the two ways that is? For example, you consider something like this. For example, we have a black box, something like this. Consider this is a digital circuit. I think it's better to write shapes. Okay, so this is a digital circuit uh, having some one input, second input. Let us consider this the third input, fourth input. Okay, so what we can see any a digital circuit look like something like this. Okay, there is a black box type something like this. We have some input and outputs are there. Okay, so any digital circuit can be visualized as, or it can be treated as either external view, it can visualize it in the external view, or it can be viewed as, sorry, think better. Okay, and another one is internal view, right? So therefore, any digital circuit can be visualized in this method only. What is the external view of your digital circuit? What is the internal view of your digital circuit? Right? So let us consider what is the external view. Okay. So the external view is nothing but, as all of you know that, it is an input and outputs. Inputs and output. అంతేనా? సో మనకి బ్లాక్ డయాగ్రామ్కి మనకి ఏం కనిపిస్తుంది? ఎక్స్టర్నల్ వ్యూ అనగానే మనకు కనిపించేది ఇది ఇన్పుట్స్ అవ్వచ్చు, అవుట్పుట్ అవ్వచ్చు. ఫర్ ఎగ్జాంపుల్, దీస్ ఆర్ కన్సిడర్డ్ యాజ్ ఇన్ ఇన్పుట్ సిగ్నల్స్, దీస్ ఆర్ కన్సిడర్డ్ as input signals, consider this is an output signals. Okay, this is an output signal, right? So therefore, inputs and outputs of any digital system can be treated as an external view. Okay, similarly, what is the internal view? Okay, that means internal view can be different forms. Internal view, what is the inside of this one, what is the inside of this one? If you want to know that, there the different ways are there. Okay, so internal view can be different ways. Different ways are there. To understand the internal circuit or internal view of the design, that the different ways are there. So let us look at what are the different internal, how can we understand the internal view of your digital circuit? Okay, that means how do we understand its behavior with the help of different methods? Okay, so let us see what are the different methods the internal view of your digital circuit can be look like. It is an internal view, right? What is the internal view? So that means understand the behavior of the circuit. Okay, internal view stands for understand the behavior of the circuit. So the behavior of the circuit can be understood by using by using gate level circuit. Okay, by using gates, or the interconnection of the gates, by looking at the interconnection of the gates, right? So I can simply write it the interconnection of gates. So by looking at the interconnection of the gates, we can understand what is the circuit is all about, right? Right. So the behavior of the behavior of the circuit is understood by the interconnection, by looking at the interconnection of the gates. Okay, for example, something like this. I will take one example. For example, we have an exclusive OR gate, something like this. One AND OR gate is something like this. One AND gate is something like this, for example. Okay. Now, so something like this. We have two input signals here. One input is here, another input is here, something like this. So by observing the internal circuitry by using the gates, we can understand what the circuit is all about, right? So by looking at the interconnection of these gates, we can say that what is the behavior of this digital circuit is. Okay, so the internal view can be in the form of a gates is the one choice, right? The next choice is that by looking at the Boolean equations, Okay, so sometimes we know that if you know the Boolean equations, for example, if you know the Boolean equation, we can identify what is the circuit is. For example, something like this, I'll write. This is the one example you consider for the interconnection of the gates. You consider another one. So that is, for example, sum is equal to AX dot B. Okay, C is equal to A and B. So people will easily identify that. People will easily identify that, okay, this is a half adder circuit. So they will perform the addition between the two operands. Okay, people can understand if the internal circuit is showing the Boolean equations, people can understand, okay, this digital circuit is all about the half adder, right? So therefore, we can view the internal circuit by using the Boolean equations also possible. Or by using the third method is that by using the functional tables. Functional tables. Or I can say that simply a truth tables, for example. So if you are using the truth table also, you are able to identify that its behavior of the circuit. The internal view can be. So the internal view can be a truth table. Okay. Or for example, A you write here, B you can write it here, sum here is carry here, 0, 0 if you write 0, 0. Okay, 0, 1 you write, 1, 0 will be the answer, 1, 0 you write, 1, 0 will be the answer, 1, 1 you write, 1, 1, 0, 1 will be the answer. Okay, so by looking at this truth table also, we say that, so we can understand the internal view of the circuit, right? Is it clear to all of you? Any digital circuit, any digital circuit can be visualized by using the external view and by using the internal view. External view is nothing but input and outputs of the digital circuit, but the internal view can be varied depending upon the availability of the information. Okay, if you know the if you know the information about the interconnection of the gates, then this is the one method that we can understand its behavior. If you know the behavior by using the Boolean equations, then we can understand its behavior. If you know the internal view by using the information called truth table, then we can understand its behavior by using the truth table, right? So this is the basic for writing a Verilog code to describe the digital circuits. Very, very important one. Okay. So if you want to write a Verilog program, this you should know. Okay. So how we can use this particular information to write a to write a Verilog program, we will see later. So according to the visualization, digital visualization, we can give a conclusion something like this. Okay. So for any digital circuit, if we talk about any digital circuit, so having some kind of input signals, having some kind of output signals. Okay, I think it's not good way to write. Okay, so the internal input and outputs is the external view. The internal view can be, it can be a gate circuit, gates, it may be a gates, or it may be a Boolean equations, or by using the truth tables, right? So this is the fundamental information that we should know while we are describing your circuits. Is it clear to all of you so far? So the concept is clear or not? Chapala, Naku. So what do you mean by how do we visualize your digital circuits? I'm talking about that one. Okay. So that is the fundamental to describe the circuit. So by the way, what do you mean by the description? Let us write what do you mean by the describing of your circuit? Okay. So just fundamental way that I will tell you that how do we describe, what do you mean by the description? What do you mean by description? What do you mean by the description? As I told you in the last class also, by giving the example. So we talk about only the digital circuit, right? We talk about only the digital circuits. Therefore, I am going to consider only the digital circuits only. Okay. So for example, we have an OR gate, something like this. We have an AND gate, something like this. and we have one NOT gate is available here in this way. For example, something like this. Okay, suppose something like this. We have a input signal here and another input signal here is, and one input is here. Another input is coming here and going out in this way. Oh, it's not good. Something like this. One AND gate, one OR gate, one exclusive OR gate, and one XNOR gate. For example, you can set in this way. So input signal here, something like this. One input is here, for another input is here, output is connected here. Another input is coming from here to here, and the output of this one is connected, this one, and take another input is here. For example, something like this. For example, A, B, C, D, and E. And we are producing one output signal by using the AND gate. Sorry. Something like this. Okay. So here, this is what a digital circuit is look like. What do you mean by the description of the circuit? Okay, which means the description of the circuit means how many number of components that we are using. The components, the number of components, especially in the form of gates I'm talking about. How many number of components that we are using, how all the gates are connected. Is it clear? So this is the two information that we should know. So this is how the description is. Not this one. Right? See what is happening here. So this, how many gates are there? So n number of gates are there. For example, this is gate 1, gate 2, gate 3, gate 4, gate 5. 5 gates are there. How it has been connected, all the gates. So the output of this first is connected to the input to the next one. So the output of the second one is connected to the input for the fourth gate. The primary input, D input, is connected to the third gate input. Something like this. We have to say that how one gate is connected to another gate with the help of wires. Okay, so this is called a description. Is it clear to all of you? What do you mean by a description? Description stands for how many number of gates are there, how each and every gate is being connected. Okay, fine. So that is called a description. So since we are describing the digital circuit, which we call it as hardware, therefore it is called hardware description. Therefore this is called hardware description. Right? So now, the hardware is described in this way, but how do we do this description? It is in the form of a language. It is in the form. So as I mentioned that the first gate input is connected to the input to the third gate. The output of the second gate is connected to the input for the fourth gate. Something like this I'm writing. So I'm telling you orally something like this. But if you write in the form of a language, we have to write this in the form of a language. Therefore, it is called hardware description language. So I will tell you how do we describe this one with the help of language. Okay. Is it clear to all of you? Hardware description language, what hardware description language says that? Please write it on the chat box. Is it clear to all of you or not? Hardware description language. Please, everyone should understand. Okay. The concepts you should understand very carefully. Okay. So this is what the description that I have given for the hardware description language. Now I will take simple example how to write a Verilog program. Okay. How do we write a Verilog program for a simple circuit so that it will be clear overall, you can understand this one. Okay. So we'll take one example, a simple program that I want to write. So with that, we can conclude the class. Okay. Simple example. Verilog, a simple Verilog program. Okay, so let us write a simple Verilog program here. Okay, so we will take in a half adder, for example, not a half adder, full adder. For the sake of simplicity, I'll consider full adder. Okay, so something like this. What does the full adder look like? Okay, the full adder is something like this. For the sake of understanding, I'm writing different colors for this one. This is a A, this is the, and this is some signal, and this is the C out signal. Please remember. So understand now the how to write a program, how I am going to describe the circuit. Please understand. Therefore, it will be it is a very fundamental, and you should know this program. And the entire course is sufficient. Entire course is will be very easy. Okay, this is the fundamental. Okay, this is the sum signal, and this is the carry signal. C out, for example. Let us consider this is called CN signal. Okay, all of you please follow these instructions, how I'm writing the program. Okay, let us give the name of this program, let us give the name of this adder is FA. Okay, okay, now please remember, if you want to write a Verilog program, first you should know that this FA, this black box, we are treating as a module. We are treating as module. All small letters only we have to use. Please remember that this black box in Verilog point of view, we are treating as module. All small letters, M-O-D-U-L-E, module. Okay, right. Now, what is this name of this module that we have to write? We have given the FA. FA is the name of the module, right? FA I have to give. Now, we should mention the external view of your design. We should mention the external view of your design. What is the external view of your design? What are the external view inputs and outputs? What are the inputs, outputs you are taking? What are the variables you are taking? A is the one external view, B, CIN, okay, sum and C out, right? These are the things. After completion of the external view, we have to write a semicolon. Since it is a programming language means we have to follow the rules and regulation framed by the Verilog. Okay, the Verilog says that once the statement is completed, we have to end with the semicolon. Okay, without writing the semicolon here, it's not possible to execute your program. Okay, this is the first step. Is it clear to all of you? Any module, any digital circuit, we are treating as a module, and we should write the name of the module. Whatever the name that we have suggested, we have to use that name. FA I have used, therefore FA I'm using. And A, B, C, N, S, C out I have to write. So this is the external signals that I'm writing. Now I should mention what about input and output, A, B, C, N, S, and out. So I should say that among all these variables, some variables are treated as input. Small letters only I have to write. Input. What are the inputs that I'm using here? A is one input, B is one input, CN is another input. So this statement is completed. I need to write a semicolon over here. Okay, right. So among all these variables, some of the things I'm treating as an output, right? I should write output list also. Output. What are the outputs here? Yes, comma, C out. Are we the other way in that? So this is the first thing. This is the first thing that we should notice. The second thing is that these two are the statements, port list that I should write. I should write the input output declarations, something like this. Next. So so far so good. So far we have seen that the external view of the design that I have done. What is the internal view of this design? So internal view of the design I'm using with the help of gates. What is the internal view of the design? Something like this. So I have an exclusive OR gate, 3 input exclusive OR gate I'm considering. Okay, so A, B, C, A, N. This is the sum signal. A, B, sorry, AND gate, another AND gate, another AND gate. Sorry, AND gate. We take another AND gate. This is an OR gate. Okay, so 1, 2, 3, 4, C out. Okay, so first one is AB. I had to write AB. I need to write, and BC I need to write. Everyone knows about the circuit. Okay, that's the reason why I'm writing very fastly. Okay, then AC is required. This is A, this is C. Okay, okay. So now this is your internal view of your design, right? This is your internal view of your design. Therefore, I can write this is A. Oh, this is called A, B, C, A, N. This is sum and C out. This is actually C out, right? So this is the internal circuitry that I'm having. Okay, so therefore I need to write the internal view of the circuitries at this place, right? So I have to write an internal view, and finally I will write a end module here. End module. Okay, so there we have to write a Verilog program, internal view of the circuit we have to write at this place. So at this place I need to write internal view. Okay, so this will be the topic of the tomorrow's class. So how do we call these gates into this particular place? We will see in the next class. Is it clear, all of you?
Yes, sir.
If you have any doubt, please ask me right now only. If it is okay, then that's fine. Okay.
Sir,
Chapande.
so can you place this recording, sir?
Yeah, I will download this one and I will share it this record. Okay.
Okay, sir. Thank you, sir.
Okay. So language is very important language. So you have a lot of opportunities are there. If you go outside of after completion of your course also, there's a lot of job opportunities are there if you learn Verilog language. That I am sure. So just if you want to learn the subject, you please follow my instructions, how I'm giving the instructions. Okay. And the textbook, what is the textbook that we have to follow? That is also I will discuss tomorrow. And this is the fundamental for the course. So this is a fundamental class for the course. So you should know this information carefully. Then from the next class onwards, we will go according to the syllabus. Okay. Because I can say that this is the orientation class. I can say that. Okay. So this lecture also, this notes also, I will put it in the GLearn. Okay. So that you can go through it once. Thank you all. You can leave the class now.